How are we doing today? Hopefully y'all are doing well. Today we are going to be starting our notes on solutions. So we're going to be continuing Unit 3, which is over intermolecular forces, and specifically we're going to be focused on solutions today. Now for this, you do need to make sure you've got your notes and something to write with. It also wouldn't hurt to have a periodic table, but those are the things that you should need for today. All right, so let's go ahead and get started on these notes. Okay, so first off, before we talk about solutions in terms of IMFs and that kind of thing, let's talk about what a solution is. Now remember, a solution is a homogeneous mixture. Now remember, homogeneous means that they are going to look the same throughout. They're going to be consistent with how they look throughout. And a solution could be solids, liquids, and gases, or gases. And so when we're looking at these, we need to keep in mind that it could be any of the states of matter that we're talking about. Okay, now we know it's a homogeneous mixture. Remember what a mixture is. A mixture is two or more things that are physically combined, okay? And so by physically combined, it means that I can also separate them physically. All right, so two or more substances physically combined. And as a result, we get a homogeneous mixture, which again should look the same throughout. Solutions are going to appear to be the same throughout. And that's in contrast to them actually containing multiple materials. So an example of this would be stuff like air or seawater. Air, we can look around and it looks the same throughout it, right? There's no different like, okay, well, that's like gray air and that's white air and that's clear air. It's very much, it looks the same throughout. We also can have something like seawater. Seawater is going to look the same throughout. Now you could actually see some things floating in the seawater, and then a lot of times we'll call that a heterogeneous mixture because it then does not look the same throughout, okay? Now, the majority of the components in a solution, so in that homogeneous mixture, are what we call the solvent. Now remember, your solvent is going to be the thing that causes something else to dissolve. The minority of this solution would be what we call a solute. And the solute is what is actually dissolving. Okay, so if I take water and I take salt, the table salt is going to dissolve in the water. So the table salt would be the solute and the water would be the solvent. Which do I have more of? Water. So the water is the solvent. Okay, now solutions form in part because of the intermolecular forces that we've got. Okay, so the attraction between the different molecules is what's going to cause these solutions to actually form. Okay, and so essentially what's happening is when you're taking a look at something like this right here, you're going to see these molecules are actually going to start to pull each other apart. Why? Because they're going to have some form of attraction that occurs. So here I've got some water, and then probably this would be our table salt, NaCl. And so what you see is you see your oxygen bonding to the positive, so the sodium, and then you see your hydrogen bonding to the chlorine, so the negative. And so that's kind of in general what's happening when we're talking about these polar substances actually pulling one another apart. Okay, so now we got a general idea of how this is actually going to occur, how these solutions are actually forming. So let's talk about solubility, okay? And when we're looking at these, remember that sometimes you can put so much stuff in something that stuff stops dissolving, right? We can put so much salt, table salt, into water that eventually that salt is going to stop dissolving. And that all comes down to solubility. Now, what is solubility? Solubility is the maximum amount of material that will dissolve in the given solvent at a given temperature. Now, we say a given temperature because temperature is going to affect that. And so we'll talk about some factors here in a little bit. But when we're looking at these, we do need to keep in mind that it is the maximum amount that can dissolve given the current situation that it's in. Okay? And that's all going to be coming down to, if we reach that point, it's what we call saturated. And again, we'll go over that here in just a second. Now, talking about our solubility, there's some terms that we need to keep in mind. First off, if we're talking about a solid or a gas, the term that we use is soluble or insoluble. Soluble means when the solute can dissolve, and insoluble means when the solute can't dissolve. Okay, so if I say table salt is soluble in water, I know that that it would be able to dissolve when I put it into water. Okay, if I were to say something like table salt is insoluble in water, then I would assume that the table salt could not dissolve in water. Now, based off of that, we know that table salt is soluble in water, and so we know that table salt will dissolve in water. All right. Now, if we're talking about a liquid, this is referring to, or what we would say is miscible or immiscible. Miscible means that those two liquids are going to be mutually soluble, and so they're both going to be dissolving at the same time, right? Versus immiscible, which means those two liquids would be not soluble or insoluble, all right? Now, if we're talking about these things, we know that some things dissolve some things and other things dissolve other things, right? We know that like water will dissolve table salt, but it won't dissolve something like wax. And why is that? Well, that all comes down to this idea that like dissolves like. Now, that is just a general observation, so we shouldn't use it for our reasoning, but like dissolves like. And what I mean by that is that if I'm talking about a polar solvent, polar solvents will dissolve polar solutes, but they will also dissolve ionic solutes. Why do we think that is? Well, a polar solvent is going to be something that has a positive and a negative side, right? We've got that dipole that's going to occur. An ionic solute is going to be something that's got a positive and negative charge that's formed that bond. Remember, ionic is just going to be a quote-unquote more polar bond, right? You've got a bond that's got so much difference in electronegativity that those electrons are pulled much closer to one side over the other, okay? And so when we talk about these polar and non-polar substances will dissolve other polar substances, whereas non-polar substances will dissolve other non-polar substances, okay? So we know that water dissolves table salt, right? And so since I know that, I need to think about, well, why does that occur? Well, water is a polar molecule. Table salt is an ionic molecule or compound. And so if I'm talking about a polar molecule and an ionic compound, I know that they've both got that positive and negative end. And if they've both got a positive and negative end, they are going to be soluble, right? Okay. Now, for this, we do need to keep in mind our solubility rules. And I would highly suggest that y'all go in and memorize these 5 rules, okay? The solubility rules for our, for solubility, right? So looking at this, our first rule says that all compounds, so any compound that we're talking about, whose cation has something from group 1 or ammonium, they are soluble no matter what. So if I've got something, one of my alkali metals, or I've got ammonia, remember ammonium is NH4 with a positive 1 charge. So if I've got something from group 1 or ammonium, they are going to be soluble no matter what ion I attach to them. Okay, so if I'm talking about sodium chloride, ammonium chloride, potassium fluoride, those are going to be soluble no matter what, as long as they have something that's group 1 or ammonium as their cation. All right, so that's the first rule. The second rule says all nitrates, chlorates, perchlorates, and acetates are soluble no matter what. So again, if I'm talking about something that's paired up with a nitrate, a chlorate, a perchlorate, or an acetate, they will always be soluble. All right. Next, we've got our chlorides, bromides, and iodides. They are soluble unless they're paired up with silver, lead, or mercury. Okay, so if I have a chloride or a bromide, and by chloride or bromide, like sodium chloride, magnesium chloride, those are going to be soluble because our rule says they are soluble. They follow the rule that says chlorides, bromides, and iodides are soluble unless they're paired up with silver, lead, or mercury 1. So for that, you do need to keep in mind, I've got a chloride, bromide, and iodide. I'm going to pretty much assume that they're going to be soluble. But I do need to recognize that if I have one of those other three things, silver, lead, or mercury 1 in there, then they will not be soluble anymore. Okay? Our next rule says all sulfates are soluble unless they're paired up with silver, lead, and mercury. Again, those three. But then it also includes calcium, strontium, and barium. So again, our sulfates are soluble, and they typically will be soluble unless they're paired up with one of those 6 things. Okay? Everything else we're going to assume is insoluble. Again, unless it's paired up with something from group 1 or ammonium. All right. So now that we've got a general idea of what our solubility rules are, let's take a quick look at a practice problem. Let's say I gave you, I don't know, let's say I've got lead nitrate. If I've got lead nitrate here, well, I've got lead, and remember, lead can be one of those things that makes something insoluble, and I've got nitrate here. So thinking back at our rules, I know that if I've got a nitrate, chlorate, perchlorate, or acetate, they are soluble no matter what. So I have a nitrate, so then this would have to be a soluble compound. Okay, and so that's what you're kind of looking for. You're looking for one of these things from our solubility rules, and if it doesn't fall into one of those things, then it's going to be insoluble. All right? All right, so let's look at some specifics here. So if I've got solubility of alcohols in water. Now, this is going to be one that's a little bit different from our solubility rules because our alcohols don't always have what would look like a polar or nonpolar bond. Alcohols are going to be soluble, however, in water. Okay, soluble in water. However, if I'm talking about a very long carbon chain of those alcohols, the longer it is, the less soluble it will be. Why is that? Well, the longer it is, the larger portion of that molecule there will be a larger portion of that molecule that will be nonpolar. And so because there's a larger portion that's nonpolar, the molecule itself will be harder to dissolve. All right, so if I'm talking about an alcohol, the larger that hydrocarbon, the larger that chain, the less soluble in water that alcohol will be. Okay? Now, for the solute solvent to mix, you have to overcome a couple of things. First off, all of the solute to solute attractive forces have to be overcome. Okay? So that would be something that we have to keep in mind. If I'm talking about one solute attracted to another solute, so I've got some nonpolar molecules or some alcohols, they're going to be attracted to each other. Why? Because on the majority of their molecule, they are going to be nonpolar. Okay? So there's going to be some attraction there. The only way that will become a solvent-solute mixture, the only way that's going to happen is if you overcome the attraction between those alcohol molecules. Okay? Now, the other option is for some of the solvent-to-solvent attractive forces to be overcome. Okay? So I can either cause the solute-to-solute, all of them, to be overcome, or the attractive forces between these solvents to be overcome. Okay? Now, both of these processes are going to be endothermic. Now, endothermic, remember, means to absorb energy. And at least some of the energy to do this comes from making new solute-to-solvent attractions. Okay? So I will take that energy. I'm going to have to add energy because that energy is going to be absorbed into those molecules. And some of that energy is then going to be used to make those new attractions, which is then going to release energy. Because anytime we see that those bonds being formed, we're going to see a release of energy. Okay? Why? Because that would mean that they are more stable. That means they've got a better use of that energy, so they require less for that energy to actually hold everything together. All right. Now, factors affecting solubility of a molecular structure. So if I'm talking about a fat-soluble vitamin, so something like vitamin A or D or E or K, those are going to be nonpolar. All right. And so since they are nonpolar, they are not going to be dissolvable in water. Well, thinking about that, if I'm talking about a fat, which would be something like a lipid, those we know are not going to be dissolved in water. I've also got water-soluble vitamins, such as vitamin B or vitamin C. Those are polar. Now, those being polar are not stored, and they have to be consumed regularly. So looking at that, you can kind of get an idea of our nonpolar molecules. They are easily able to be stored by your body, whereas our water-soluble vitamins, such as vitamin B and C, those are polar, and so as a result, they actually cannot be stored easily. All right. Now, we do have also hydrophobic and hydrophilic. Now, remember, hydrophobic means water-fearing. And so water-fearing means it's going to be repulsed by that water. It's going to get away from that water. So if I take something like a fat of some variety and I put it into water, it's going to push away from that water, and so it's going to float on that water or sink to the very bottom of that water. So it's not going to actually be dissolved there. Hydrophilic is the opposite, and so what that means is it's water-loving, so it's going to be attracted to that water. And so we would see the water readily being absorbed by whatever that solute is. Okay? All right. So we've talked about a couple of factors. Let's keep on going through those factors. All right. So the next factor that would affect our solubility would be our pressure. Now, pressure, it does depend. It depends on what I'm talking about. If I'm talking about the solubility of a gas, it is going to be higher if I increase the pressure. An example of this would be like a can of Coca-Cola. If I've got Coca-Cola, what do I notice about that can? It's very pressurized, right? They pressurize it for a reason. It's not just there because they felt like it would be fun for it to go when they open up the can, right? It's actually there to make sure that the carbon dioxide stays dissolved inside of the Coca-Cola. Now, if we're talking about the effect of pressure on liquids and solids, it actually has very little effect on them. And that's because those molecules are already very, very close together. If we're talking about a gas, increasing our pressure is going to increase how close those decrease the distance between those gas molecules. And so as a result, there's going to be more solute-solvent contact. And if there's more contact, it's more likely for them to actually go through that the dissolving process. Okay? Now, Henry's law essentially just says the amount of gas dissolved in a solution is directly proportional to the pressure. So if I keep increasing the pressure, I'm going to be able to keep increasing the amount of gas that can be dissolved. Okay? Okay, so let's talk about temperature. Now, temperature, the amount of solute that will dissolve, usually increases with an increase in temperature. But it could also decrease. And so we do need to kind of keep that in mind. And we'll talk about some of those times that it does decrease. Now, in general, if I'm talking about increasing the temperature and increasing the solubility, that's going to happen in an endothermic reaction. So solubility occurs quicker if the temperature is increasing, if I'm talking about an endothermic reaction. Now, if I'm talking about an exothermic reaction, the solubility will generally decrease with a decrease in the temperature. All right. Now, here is potassium hydroxide, and sodium sulfate. Now, those three compounds, those are actually going to become less soluble as the temperature rises. So instead of following that other rule, like we said, where solubility increases with the temperature, they are actually going to do the opposite. So if my temperature rises, those three compounds, their solubility is going to decrease. Okay, and that's all explained with Le Chatelier's principle. All right, now if I'm talking about the solubility of a gas in a liquid, it will always decrease with an increase in the temperature. And a lot of times you can think of this with like a can of Coca-Cola. If I heat up a can of Coca-Cola, it actually becomes flat much, much quicker than if I were to leave it in the fridge. All right. And so like if you're drinking a can of Coca-Cola or Dr. Pepper or whatever, and you're out by the pool and you set it on the hot concrete, that can of Coca-Cola will get flat very, very quickly. Versus if you have it sitting inside of like a cooler, it will stay fresh for a much longer period of time. All right. All right. Now let's talk about vapor pressure lowering. So with our vapor pressure, while I'm talking about the presence of a volatile solute, and by volatile solute, I mean more volatile than the solvent, while the presence of the volatile solute increases the vapor pressure of the solution, the presence of a non-volatile solute lowers the vapor pressure of the solvent. Now, this is because the dissolved non-volatile solute decreases the number of solvent molecules per unit volume. Okay, so essentially, just because we've got non-volatile solutes, we're going to be decreasing how many solvent molecules there's going to be actually present there. Okay. Now, there are fewer solvent molecules on the surface because, again, those non-volatile solutes are preventing them from being there, right? And so because of that, we're going to see a decrease in that vapor pressure. All right. Okay. Now, liquid to liquid solutions. Now, remember, this is when we talked about miscible and immiscible. So if I'm talking about a liquid to liquid solution, solutions in which I've got a solute and a solvent, where they are both the liquids, right? So both liquids are acting as the solute and the solvent, and those liquids are volatile but do not behave ideally. They are both going to actually be contributing to our vapor pressure. So you've got equal amounts of both of those. They're acting both as a solute and a solvent. Both are actually going to be contributing to that vapor pressure. Now, if we're talking about a solute, so you've got less of one over the other. If the solute is more volatile than the solvent, the vapor pressure of our overall solution is actually going to be higher. Okay. All right. So now we've kind of gone through all of our exceptions and the factors that affect our solubility. So let's actually talk about these solutions that are made. So there's three big types of solutions made. There's a saturated solution. So a saturated solution is where it contains the maximum amount of solute that it can dissolve under a given set of conditions. Now remember, those conditions could be changed based off of, for instance, changing my pressure or changing my temperature, right? We know those affect how likely or how soluble things are. So a saturated solution, if we're talking about a given set of conditions, a saturated solution means it's got the maximum amount dissolved. Okay? Unsaturated solutions would mean it would have less than the maximum amount. So you put a little bit in, and it dissolves everything, but you could definitely put more of that solute in the solution. Okay? The last one is a supersaturated solution. Now, a supersaturated solution is typically prepared by us taking a saturated solution, heating it up, adding more of the solute, because again, when we increase the temperature, a lot of times you're going to be increasing the solubility, right? So we're going to heat it up, dissolve more of that solute into our solution, and then we're going to let it cool back down. Okay. Now, when that happens, we have what's called a supersaturated solution. Now, supersaturated solutions are very, very unstable. And by unstable, mean just by adding a very small portion of that substance again, what we'll see is we'll see a lot of the excess crystallize out almost immediately. And so in the real world, what this looks like is if I've got a supersaturated solution of, for instance, salt water. I heated it up, I added some more salt, and then I cooled it back down. If I take that supersaturated solution and drop a little bit of salt in there, all of a sudden, a lot of the other salt is going to form new crystals that are going to look like little rain falling down throughout that solution. Or sometimes it'll look like little snowflakes that are forming on the glass. And so A supersaturated solution is just when we have way more solute dissolved in the solution than we should actually be able to. Okay. Now, this right here is called a solubility curve. Now, for our solubility curve, what you'll notice is that our different substances have a different amount that can be dissolved in that water, right? And when we change our temperature, we're also going to be changing how much of that solute can actually dissolve. Now, one thing I did want to note, your gases, they're going to have a decrease in solubility when we increase our temperature. So looking at our solubility curve here, we should be able to identify what is a gas. Well, this is the only one that had a decrease in my solubility, so that would tell me that that is a gas. All right? Okay, now, almost through our notes on solubility and solutions, so let's take a look at this. Now, energy's involved in solution formation, so we're making these solutions. Now, whether or not a solute or dissolves in a solvent does depend on three big things with our intermolecular forces. First off, the attraction of the solute particles to one another. So salt attracted to salt. Rubbing alcohol attracted to rubbing alcohol. So those solute to solute particles attracted to one another. The next is the attraction of the solvent to the solvent. So water attracted to another water molecule. Okay? And the last is the attraction of the solute particles to the solvent particles. So essentially all of these have to kind of come together to get what we call a heat of the solution. And this is either going to be a release of heat, release of energy, or it's going to be an addition of heat or addition of energy. So we're either going to be absorbing energy or we're going to be releasing energy. So looking at this, again, this is kind of just a visual representation. This is called a particulate diagram. I've got my water. So these are my waters. And those waters are attaching to the sodium and the chlorine, and they're going to be pulling it apart. Again, recognizing that here I've got a positive end. So this is all positive. And it was attracted to the negative chlorine there. Why? Because they're opposite charges, right? And so we know that this substance is ionic and this substance is a polar covalent compound. And so because of that, they are actually able to be attracted to one another. All right. Now, again, we talked about these energies involved in the solution formation. So let's take a look at what that actually looks like. So we call that the heat of the solution. Okay. So delta H of the solution. Now, this is the enthalpy change. Enthalpy is going to be that change in heat associated with the formation of a solution. All right, so we got three steps here. We got our change in heat of a solution equals the change in heat for the first step, the change in heat for the second step, and then the change in heat for the third step. Okay, so our three steps were attraction of the solute particles to one another, attraction of the solvent particles to one another, and attraction of the solute to the solvent. So step one is going to be breaking up the solute. So we're going to be overcoming the attractive forces between the solute. Now that's going to be endothermic. Why? Because we're actually separating those bonds. Okay, and so to separate those bonds, we're going to have to add energy. Now when we do that, we're expanding the solute out. And that's what we see here, right? If we see our chlorines, they were all in a clump over here, but now they're actually being moved out and around. Same thing with our sodiums, getting out and around. So we're spreading out that solute. We're expanding that solute. Now, this is going to be very high in ionic and polar solutes. So we're going to have very high energy if we're talking about an ionic or a polar solute. Whereas if we're talking about a non-polar solute, it's going to be very low. Okay. The next is going to be the breaking up of the solvent. Again, anytime we're breaking that bond, that's going to be an endothermic reaction. Okay. So we're breaking up that solvent. Again, this is going to be very high in polar solvents and very low in non-polar solvents. Now, why did we not put ionic there? Well, that's because ionic are typically going to be solid at room temperature, right? And so we're not going to actually see that occurring with this, okay? Next, step 3, the interaction of our solute and solvent. So this is where we've got our solute and our solvent, and they're actually forming a bond with one another. And so that's going to actually be an exothermic reaction, because anytime we form that bond, all the excess energy is released. All right. And so we're releasing that excess energy, which is going to end up being very high in our high negative number in the polar to polar bonds and a low negative number in everything else. Okay. So if I'm talking about a polar to polar bond that's forming, it's going to be very high. Whereas if I'm talking about anything else, that negative number is going to be very low. All right. Why is it negative? It's negative because that energy is being released. Okay. So then we would take our change in heat of the second plus the change in heat of the third, and that would be called what we call, that would be what we call our enthalpy of hydration. So it's taking our water and it's dissolving the substance, and then we're getting that new bond that's formed. That's the enthalpy of hydration. Why? Because that solute is being hydrated by the water. Okay. Okay, very last thing. Now, this is just kind of a general, I guess, synopsis of what we talked about here with the change in heat. Most heats of solutions are positive. So in the end, most of the time when we're talking about the change in heat, that delta H of the solution, it's going to be an endothermic reaction. Now, the reason that the solute dissolves is that the solution process usually increases our entropy. So just a part of creating that solution, we're going to be increasing the entropy. And remember, entropy is just disorder. Now, what this does is this actually makes this process what we call thermodynamically favorable. So it's thermodynamically favorable. And the process involves two factors. The first off is going to be the change of heat, and the second is going to be the change in entropy. And the relative sizes of those numbers is actually going to determine whether or not a solute is able to dissolve in a solvent. Okay, so essentially, if we're looking at all those numbers and we're comparing everything, if we're comparing their sizes, that is going to be what determines whether or not something will actually dissolve in the grand scheme of things. Okay. All right, y'all. I know that was a lot, but we are through it. So if y'all have any questions, don't hesitate to reach out and let us know. Otherwise, y'all have a great rest of the day. Bye, y'all.